we go. Get the chatting going here. Hello! Hello, everybody! How's everybody doing? Yes! Yes! Yes, yes, yes. Hello! Here for some statistics, baby! Let's do some stats today! Don't mind some stats today. I hope you don't either. Should probably put a space between those. Should probably put a space between. That's all. Alright, hello, hello, hello. Hopefully we'll have some more people join. Ooh, yeah. Oh boy. About 10 minutes, alright. Yum, yum, yum. Some jasmine tea this time. Hopefully everybody's doing really well here today. Yes, yes, yes. Yes, indeed. Ladies and gentlemen, yes, indeed. Ooh, Oh, well. Hey, Kristen, how are you? This is stopping by and say hello. Well, I'll say hello to you as well. I hope today's class went well for you. I hope you were able to understand most of what I was trying to say. Things were a bit tricky today, I won't lie. But I hope you picked up on it at the very least. You don't understand anything in your classes. Aw, man, that stinks, Sixer. So what happened? How did we get to the point where we don't understand anything in your classes? You're failing algebra with the 44, bruh. Bruh, that's rough. Can I give you a little advice there, Sixer? If I'm allowed to, anyway. I can help you a little bit with algebra, at the very least. I know algebra fairly well. Well, if I were to put algebra into one word, and let me put this in the chat for you. Algebra always equals one word. Algebra always equals balance. Anytime you're doing algebra, you're just playing a zero-sum game. You're always balancing something out. Okay, whether if you have, say, you know, if you take 2x plus 5 equals 7, for example, you know, let's just go with something like that, Sixer. Balance here is actually something that you'd want to do. Essentially, it's like saying, I want to solve for x in this situation. So at the end of the day, I want to get x by itself. I said, okay, that's fair. All right, absolutely, this is what I want. All right, so the question is, well, how do I go ahead and do that here? Well, let's take a look at the big board here for a second for you. Okay, so the way you would do that here specifically is basically you would say, all right, I have certain roadblocks in my way. The first roadblock in your way would be, say, the plus 5. And you say, well, I don't want the plus 5 there. So how do I get rid of the plus 5? Well, I need to balance it out, meaning I need to do the opposite of plus 5. Well, the opposite of plus 5 is minus 5, so I would subtract 5. But I have to balance. What I have to do on one side of the equation is what I have to do on the other side of the equation. So if I'm going to minus 5 on the left side, I need to do that on the right side as well. And so I have 7 minus 5 here, which is 2. Then I have 2x is equal to 2. Then you just answer the same questions again. I still need to get x by itself, but what's my roadblock in the way? My roadblock is this 2 in front of the x. This is 2 times x. Well, how do I get rid of 2 times x? Well, I do the opposite of times, which is divide. So all I do is divide by 2. But the consequence is I have to balance. If I divide by 2 on one side, I have to divide by 2 on the other side just as well. Cancel out the 2's, and then I'm left with exactly what I want at the end of the day, which is x is equal to 1. Okay? So, although this is, maybe you know how to do this problem, or maybe not. It doesn't matter. This is a good example about where balance can be really achieved and what you're really trying to do in a lot of different types of problems. All right? Essentially, you're just moving stuff around and trying to get what you want at the end of the day. Yeah, there's some processes and stuff behind a lot of those different concepts, but it's not as bad as it may seem. But that's why I always go with the idea of the word balance there, Sixer. Hey, ninjas, how you doing? How you doing, my friend? I hope you're doing really well, my dude. We're just talking about some balance there. All right? Talking about algebra and balance and how important that is. I'm doing extremely well, ninjas. Today has been a very productive day. I got a lot done, a lot accomplished today, that's for sure. Been very, very busy. A lot of schoolwork and stuff that you have to catch up with, but yeah, it wasn't too bad. I still got more work to do, but that stuff is pretty easy. So that shouldn't take me too much time. Yeah, how about you, man? What have you been up to? You know, the weather's getting nice out there, ninjas. I'm sure that this is a good time to go out, for a nice ATV ride or a hunt. I have a colleague of mine that's actually going up to the upper parts of Wisconsin there, and doing some duck hunting out there. So, hey, no problem, Sixer. I just hope my advice is helpful for you, my friend. That's all. I would like you to do and see you do better. Obviously, I know that's not something that you want, but I'm here to help you. Hopefully get better. That's that's why I'm here. Sadly, no hunting, but April's turkey season. So, ooh, very nice, very nice. Got a month to go. Definitely a month to go. Well, I think you're in a good. I think with this season, it's actually surprisingly enough, at least here in the Chicago area, spring actually started earlier than I thought. Because usually spring starts a little bit later in March, but this year it's actually earlier than what it normally is. I mean, today was like 63 degrees outside. It was wonderful, absolutely gorgeous out there. I'm not gonna lie. I mean, I stepped outside. I'm like, I don't even need my jacket. I said, I can't believe this. This is unbelievable. About 70. Woo! My friend, 70. Very nice, very nice. Mazdy, how you doing, my dude? How we doing, my friend? I hope you're doing well. Straight chilling like a villain? I can respect that. Respect! I can respect that. Awesome. Did you have a good weekend? Hope you had a great weekend. It was, Oh, man! Aw, Ninjas, you didn't have to do... Aw, man. Ninjas, thank you for the gift sub. Oh, my goodness, Ninjas. You didn't have to do that, my dude. That's so super kind of you. Oh, my goodness. Oh, you didn't even have to sub to my channel. Shoot, dude. Ah, man. Ah, man, that's so... Oh, man, that's super nice of you. Thank you, Ninjas. That's... Man, I don't know what to say to that. That's... I don't know if I deserve something like that, to be honest. I'm just a regular math scrub. I'm a math teacher that just likes to have a little bit of fun. Thank you so much, Ninjas. You're really, really super kind. I hope that at some point I get to meet you in person and we can sit back and kick back a few brews. So, thanks, my friend. Thanks so much. I definitely owe you a brew, man. Definitely owe you a brew. Pretty sure a nice beer is definitely in the works for you, my friend. You've done me a solid. I can't argue with that. Thank you. And you're super nice, super kind. Oh man. Yeah, we do gotta get on a game soon. Yeah, I've been playing some COD with James. I've been playing some COD there. So I've been trying to get better at COD. Trying to. Not zombies per se, but I've been playing some some regular multiplayer, like like the domination maps or like Apocalypse 24/7. Just trying to level up my guns and stuff. Hey Susan, good morning, good evenings, good afternoon, whatever you want to call it. I was like, good morning. Like, what am I doing? Hello. Camera, good evening to you. Natty, hello. Holly, hello. How are you doing? How are you doing? Let me tell you, it's 6 p.m. and I don't even know what... Like, I've done the intro twice in a row this morning, and I felt it was Wednesday for some reason. I don't even understand why that even happened. But I was like, it's Wednesday. I'm like, no, it's not Wednesday. It's Monday. It doesn't feel like a Monday. It feels like a Wednesday, like a middle of the week for me. I don't understand. I don't get it. But it's just like I'm here. It's Monday, but you know what? With everybody here that comes to the stream, like my friend Ninja's there, like all you guys that come to the stream, it never feels like a Monday. It's never bleh. Okay? It's never bleh. Yeah, time goes by. I agree, my friend. Time slips by like it's nothing. I don't disagree. But you know what? Mondays are usually the blehs. But with you guys, it's never the blehs. It's always the funs. And so it always feels like it's the middle week. Like I've kind of it's the mood's already been set. We've already been kind of straight chilling. You know, even though it's like the first time we're meeting once again this week. So I mean, that's what makes this even more enjoyable. Look at this. The vibes. Let me tell you, ladies and gentlemen, the vibes. Okay, absolutely outstanding. Okay, 100,000% absolutely outstanding. Okay, I cannot argue with any of that. And look what I got next to me too. I got some wonderful. I decided to go. I went to Mitsuwa this weekend. Got me myself a different 2-liter bottle this time. I got myself a jasmine. I got myself a jasmine green tea 2-liter bottle. Okay. Yes. All right. I finished my other 2-liter bottle. I got 2 more sitting in the fridge. This was one of them. Some jasmine unsweetened green tea, ladies and gentlemen. Nice and cold. And what are you drinking there, ninjas? I don't... You're drinking bourbon, okay. Well, how about this? You know what? Jasmine green tea is really unique because it's not as bitter as like the other regular type of green tea or cha. This stuff is just like bourbon. It goes down real smooth. All right. So, yes, there you go. Uh, I'm sure that we have it's 2 different drinks, but they have both the same qualities, nice and smooth. Oof. I'm not sure if Jasmine clears the sinuses per se, but still, you know, smoothing it. Gotta do the action, be like, yeah. uh, you know, I do have a sub goal. I don't even know if that sub goal. Man, I don't even know about that sub goal. Let me check out my other thing, my big board with the sub goal on it. Oh yeah, that needs to be updated. Holy smokes. Okay. I do have a sub goal actually, out of all things. Let's end the goal here. So maybe I pick a new sub goal. Yeah, I don't know. We'll pick a sub goal of 14. Oh, actually, we'll pick 15. Oh, I see. I gotcha. I gotcha. We'll go with that. That's the. I don't bring up this screen too often, but yeah, we'll bring up the sub goal there of. I currently have 12 subs, which is more subs than I ever thought would be even possible, even like a few months ago. So, it's just people are too kind to me. So, all right, but we gotta get to work. That's how it has to roll. Let's get to work. Yeah. All right, we gotta get the intros done. Let's do these intros. Let's do these intros. Let's get this party started. Let's do this, ladies and gentlemen. All right. Thumbs up, let's do this. All right. Let's go. Okay, let's get started today. Welcome back to Monday. Hopefully, you're a nice weekend. I got it right this time. All right, welcome back to Monday. Hope you're a nice weekend. So, today, ladies and gentlemen, today we are getting into a brand new chapter here. We're getting into chapter 7. Okay, chapter 7 is what we're doing here today. Now, luckily for you guys, I had a good look at chapter 7 before I started class. I wanted to get a good look here, just going over all the little bits and pieces about what we're going to be talking about. And so I looked at one section, section 7.3. 7.3 is a section where I'm going to talk about section 7.3, But what I'm going to do here in regards to section 7.3 is I'm not going to have you do any homework related to it. I may just end up giving you 5 free points for that particular section, and then we can move on like regular people at the end of the day. So, yes, you'll get 5 free homework points for section 7.3, and sections 7.1 and 7.2 will be the two sections there of chapter 7 that will actually have homework associated with it in some form or fashion. All right, so I think that seems fair. If you don't like it, I don't know what to tell you. But, yeah, reasons. We'll just gotta run with it. All right, but before we go ahead and get started with the new sections here today, does anybody have any questions? Um, any questions from last week? Any questions from last week, anyone? No? Okay. Nope. Okay, okay. You did, but you forgot. Okay. When it comes back to you, Natty, just let me know, okay? All right. Okay, cool. All right. So let's go over today's handout here from section for sections 7.1 and 7.2 here. Today, all right, let's talk about what we did last time. In section 6.2, that was the last section that we did. We talked about a binomial distribution. Even in section 6.1, we talked about a probability distribution. So we've been talking about particular distributions here in chapter 6. Now, chapter 7 deals with one particular type of distribution once again, but one that actually has even more implications than the first two. That is going to be the normal distribution. Now, we've seen a normal distribution before in the past, but let's go ahead and go to the other screen here. Go. All right. And with the normal distribution, this will be like what we call a normal distribution is a specific type of distribution, and it will be underneath what we call a probability density curve, okay? So let's take a look here at what a generic probability density curve is and how the normal distribution actually fits within this context. Okay, so some of these questions here are going to go rather quick. It's not going to be too bad, but I promise you going to be pretty straightforward. Let's go ahead and do this out. So number one, what is a probability density curve? So it's a curve that represents probabilities of all possible continuous random variables. So here's the one key difference between what we did back in chapter 6 and what we do here in chapter 7. Chapter 6 deals with discrete random variables. Now here we can deal with continuous random variables. Okay, so now it can take on any value. However, it's in the form of a curve since they're not just, dots in a row. We can just take a line and just graph it out. All right, now, some properties of the probability density curve, as you can see here for number 2, are the same properties that we've talked about already ad infinitum about probabilities. So for example, the total area underneath the curve is equal to 1. So that has to be true. 100%, if you add up all that area underneath the curve, it's going to add up to 100% like all the probabilities you would normally have. Nothing's changing there. You either you go from 0 to 100. That's all you deal with, or 0 to 1. That's all you deal with. All right. So again, that has to be true. The second one here also is true, is that the height of the graph must be greater than or equal to 0. So again, has to go from 0% to 100%, or 0 to 1 for probabilities. So they can't be negative, right? We talked about it before. Probabilities can't be negative. That's not possible. And probabilities can't be above 1. That's not possible. Okay, so that's where number 2 kind of falls into play. It just reiterates the same things that we've talked about before. Nothing changes in terms of what we've talked about. So, okay, those are generic probability density curves, all right? Same stuff, just repackaged in different words. That's about it. Okay, now, the important part here comes up next. Okay, so what is a normal distribution curve? So a normal distribution curve is a curve that is normal in shape, i.e. the bell-shaped curve. So if you remember here, the bell-shaped curve, let's go over this really quick. The bell-shaped curve looked like this, right? Kind of looked like this. There's the bell-shaped curve. We talked about it before, early on, back in I believe chapter 3. So we talked about this in chapter 3. We talked about a property regarding that, which will come up here today. But that's generically what the normal distribution looks like. Again, it has some properties certainly associated with it, which we'll go over now. So put this picture up here, and then we'll go over the properties here. So what are some important properties associated with the normal distribution curve? Let's take a look at that here. So number 4, what is the properties? So letter A, the curve is symmetric about the mean. So meaning to say we can cut this curve in half, and we talked about it before in chapter 3. I know it's been a while though, to be fair. But we can cut this in half 50-50. You got 50% on the left, 50% on the right of the mean of whatever you got there, just fine. The area underneath the total curve, just like we talked about before, it is a density curve, probability density curve, so it's still the area underneath the total curve is 1 or 100%. It's symmetric, so we talked about that before, 50-50 on both sides. And it follows the 68, 95, 99.7 rule, aka the empirical rule. We talked about this rule here again also in chapter 3. That's where we got those bars and those percentages. We said, okay, what's the percentage data items, 1 standard deviation away from the mean and whatnot. So we talked about that rule there quite a while ago. So if we go to, I believe it was one of the last sections, maybe let me check which section that was in. Okay, should probably put that there. Yeah, so this was section 3.2. So we saw this in section 3.2. I'm actually going to move this up here so it'll be in your notes. Elemental Master, thank you for the follow. Appreciate you, buddy. Appreciate you, my friend. Nobody, but I did it anyway. I'm just a rebel like that. I figured it would be a nice thing to do, Elemental Master. I don't know. I don't know what you want, but since you don't want it either way, I'll just do what I want anyway, and then we'll just kind of have to run with it. So, section 3.2. All right. So, section 3.2 is where we found the 68, 95, 99.7 rule. All right. All righty. All right. So let's take a good look here at this curves here for just a second. We're going to take a look at the book. Let's take a look at the book here. All right. Okay, so all we need to do here is recognize if a curve if a model would be considered a normal curve or would it not be considered a normal curve. All right, so all I want you to do here is just take a look at these examples here. I want you to just tell me yes or no. Okay, it's that simple. Tell me if it's normal or tell me if it's not, yes or no. So let's look at number 19. Number 19, is this pretty close to normal or no? Yes or no? Number 19, that's right over here. Number 19, yes or no? What do you guys think? Yes, normal. No, not normal. What do you guys think? Yes? Okay. So I would agree here that number 19 would definitely be yes. Okay, it looks like a bell-shaped curve. This would be normal. That's fine. How about number 20? Number 20, yes or no? Number 20, yes or no? Go ahead and type that out in the chat. That normal? No, yes, no. Okay, so the answer is going to be no. Okay, fine. Number 21, yes or no? 21, yes or no? No? Oh, okay. Can't argue there. How about 22? Yes or no? Okay. All right, great. That's yeah, good. Good job. Great work, everybody. In a sense, that's pretty much section 7-1. That's most of 7-1, honestly speaking. Is all you have to do is look at graphs, be like, does this look normal? Does this look like a bell-shaped curve? Be like, yeah. Hey. Does this look like a bell-shaped curve? No. Cool. Yeah. Yeah, that's section 7-1 in a nutshell, to be perfectly honest. Like that's all you really have to honestly really remember. Really not too hard. I know, wow, right? Like if this was face to face, like dead serious, if this was face to face, okay, I would just be showing you the book like this, right? I had the book like this and be like, hey, yes, no, yes, no, yes, no. You know, I'd be pointing to it. If it was face to face, do it the same way. There's like literally no difference. There's like not much to talk about outside of that, in all honesty. Because what we wanted to, I know, because what we want to do here is actually apply it, you know, in certain situations, right? We kind of have a good idea already about what a normal distribution is from section 3.2. So it's like, well, we're just kind of, I don't know, beating a dead horse at this point. So I'm like, yeah, I'm not going to spend a whole ton of time here, but it gives you a good idea about how you know, probability density curves can look. Either they're normal or again they look like something else, like skewed left, skewed right, whatever you want to call it. In any case, um, let's go ahead and take a look here at the next question on the handout. Some lessons, man, some lessons, some sections, let me tell you. All right. So, next is really where the things are going to, where the meat and potatoes of today's set lesson is going to lie. So, yeah, wow, look at that. I finished in 15 minutes. Dang. All right. It's actually just as fast as I would do in my regular class. All right. So, actually, no, that's a little slower. I'd finish in about 7 to 10 minutes. All right. Anyway, I digress. All right. Number 5, how can we use the z-score to find the area underneath the curve? Okay, so what we're going to talk about now here is we're going to now talk about how we can apply and find probabilities using the normal distribution curve. Now, we talked about z-scores a while ago. Now, you're probably saying, whoa, 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 z-scores, what was that again? What did that actually mean? Okay, fortunately, before we get to what's written up here on the screen, we're going to go ahead and take a look and reiterate ourselves about z-scores here. I'm going to skip down here to the bottom into number 7 and number 8 here on the handout. Okay. Um, Number 7 says, well, how do we find a z-score with a mean and standard deviation? So remember that a z-score here is equivalent to the data item minus the mean divided by the standard deviation. So remember, a z-score was related to each individual data item, depending on whatever the mean and standard deviation was of that particular distribution. Okay, so that's the formula that we have associated with that here. Data item minus mean, all that divided by the standard deviation. What are some properties of z-scores? Well, what does a z-score mean? A z-score represents how many standard deviations a data item is from the mean, right? Right. So again, one of the big properties here is that again, z-scores z-scores can be negative. All right. So remember that z-scores can be negative. So we could have positive z-scores. We could have negative z-scores. Um, each z-score is unique to its respective data item. So that was another property of z-scores that we had talked about from before. And each z-score here can be linked to a percentile. All right, so we did talk about percentile just a little bit here last time. And each z-score that we have here, depending on the sample size, okay, so depending on sample size, actually, I should take that back. I'll just put percentile for now just to keep things as easy as possible. Let's just go with that. Each z-score can be linked to a percentile. I think I'll make things more complicated if I add a little more. All right. In any case, those are some important properties of z-scores that we are specifically going to be looking at here in section 7.2 here today. All right. So let's talk about how we can do that. And let's see what we're working with here. Now, let me go back up here to, yeah, we'll get that here. If you, yeah, one more thing here. Again, how do we find a data point associated with the z-score? A data item can be equal to the z-score times the standard deviation plus the mean. So that's pretty much how you can do that. You just do a little bit of algebra with the formula, and that's how you can find the data item associated with the z-score. Now, we're not going to do much with that part there as much as we are going to be doing with the other guys. So, oh, okay. Get to that section there. Go. Okay. So what I want to focus on here instead is I want to focus on one particular question here to start with. So I'm going to go to that guy first. All right. Okay. So we're going to go over these questions right here for section 7.2. These are the examples that I want to focus on here because a lot of the things that we're going to be doing here today are going to revolve around getting around these particular concepts. All right. Let's take a look here at question number 5. Okay. And we'll talk about the wording here again. Just like we had from before, the wording here is going to make a significant difference. So let's talk about how that works. Okay, so first number 5 here, determine the area underneath the standard normal curve that lies to the left of negative z is equal to negative 2.45. All right, so let me wipe this out here because I'm going to need a few things associated with this. Determine the area underneath the standard normal curve that lies to the left of negative 2.45. Now, what does that mean? As a picture, what does this mean? This picture here says here's the standard normal curve. It looks like this. Let's say this part here happens to be z is equal to negative 2.45, somewhere over here. I want to find the area that's to the left of that particular mark. So all this stuff that I'm going to shade in black. I want to find out what this area is. Now, unfortunately for us here, we don't have the 68, 95, 99.7 rule to really help ourselves out. Unfortunately, negative 2.45 is kind of awkward to work with. So we're going to need to do something else in order to get that done. All right. Now, in order for us to get that done appropriately, we're going to need to use a little guy. So this is the part where we definitely want to write stuff down. All right. So definitely this should be definitely in your notes here. So let's look at number 5. How can we use the z-score to find the area underneath the curve? We're going to use a calculator function here. That calculator function here in this case is what we call normal CDF. Okay, normal CDF. Okay, now you're probably wondering, where the heck do I find normal CDF? Where is this thing that you call normal CDF? That is a wonderful question, and one that I plan on answering right now. Calculator up. All right. All right. So if you recall last time we did the binomial distribution, we're going to go back to that same submenu here. Okay. So I want you to hit the second key and the vars key. So the second key and the vars key, the VARS vars key. And we're going to get to this menu right here. And you see right here at the top, you see number 2 is normal CDF. Okay. I want to point something out here very quickly. Okay, and I will add this as a note here to this particular handout, and you should add this as well. Hey, Dory, how are you, my friend? Hope you're doing well. At no time in this course, all right, normal PDF. Now, I know we had talked about binomial PDF and CDF last time, but we are not, N-O-T not, okay? So, very good. Normal PDF will never be used, okay? Not in this class, okay? So you at no time should you ever use normal PDF. That should never be used in this course, like ever. Okay, so we are only going to use 2 out of the first 3 options. We're only going to use 2 out of the first 3 options, and number 1 isn't it, okay? That only leaves you with the other 2 options, which will be used, numbers 2 and 3. We'll talk about number 3 here a little bit in a second here. Okay, so number 2, number 3 here, definitely those are the guys. Okay. Dory, you're too good for me, Dory. I just know that already. Um, you're too smart for everybody, Dory. That's why I know you'll be very happy with this lesson. Got that right. See, you're too smart for me, Dory. Too smart for me. So we're gonna use normal CDF here. Okay, we're gonna use normal CDF here. So I'm gonna switch over here to let's switch here to the no face cam. Let's get to the no face cam here for a second. So now we're gonna switch to normal CDF here. And so here we got 4 things, okay? We got 4 things we have to focus on here, all right? So let's go back to the thing here. So here we have the lower value, the upper value, the mean, and the standard deviation, all right? So we have the lower value, the upper value, the mean, and standard deviation. That is what the 4 values here underneath normal CDF will be. Now, I do have to point this out here specifically, and that is if you have the old school calculator, the older version of the calculator, older software, you will need to know what the formatting is, okay, these 4 values here respectively. If you have the newer style calculator, the newer TI 8384s, then you'll see exactly what you see here on the screen. All right, and then it'll format it for you, no problem. Now, one of the things that we are talking about here in this particular example is that we're trying to find everything in a box to the left here. All right, that's what we're trying to do. All right, Beyonce got it right. All right, I'm just saying. Saying. How would you format it for an older calculator? It's exactly as you see it here on the screen. All right, it's pretty much the calculator. Like these are like shortcuts because it has a little sub menu here. For an older calculator, it'll show you nothing. So basically, my calculator is the older calculator, so I can show you. So all you would see on your screen is basically this. This is what you would see on your screen. This is what you would see on your screen. You see like normal CDF. This is all you see on the screen. You see normal CDF, and then you have this is what you would see on your screen. Just this. And then you'd have to know that you need to put in those 4 numbers respectively. That's why I included this here. That's why I've included this part here that I'm highlighting. That way you would know what each of the numbers here would represent if you didn't have the submenu there for you. All right, Mazdi? It's important there. So, yes, that's correct. Yes. Yes. You're correct there, Mazdi. You would separate it by commas, correct. So if you have the older style calculator because you borrowed it from a friend and it's pretty old, then that's perfectly fine. That's why I go over both here because I totally understand that some people have one version or the other. Okay. So I'm going over this carefully here so that way it's again it should be easier to digest for both sides. Okay. Now to add to that here, specifically to add to that back here. Okay, so to add to this here, we have below or less, okay? Or I can also put the word left, okay? So below, less, or left, we're going to use this value right here, okay? We're going to use normal CDF, negative 1 e to the 99, and I'll show you how to do that here in just a second. The upper value here, and we'll put 0, and we'll put 1. Now, 0 and 1 here basically is if you're not given a mean or standard deviation in the problem. So if you are not given any mean or any standard deviation in the problem, then you can use these 2 default values here to replace them. So 0 is the default mean and 1 is the default standard deviation if you are not given a mean and standard deviation. So I'll put that in here. If not given a standard deviation. All right. Now, if you have the words above, more, or to the right, then you would use normal CDF, the lower value, 1 e to the 99, 0, and 1 here, respectively. Okay, again, 0 and 1 still being your standard default values. Now, the real question is, how do you get negative 1 e to the 99 or 1 e to the 99 to show up on your calculator? So that's kind of the real crux of the issue here. So I'm going to delete this out here, and I'm going to show you how you would do this on the calculator manually. Because what happens if you accidentally delete it out or you accidentally overwrite it? You're probably saying, well, what do I do? How do I enter that in? All right. So the way we want to do this here is we're going to go ahead and hit in this case, we want minus 1 e to the 99. So we're going to put minus 1. All right. Remember not to hit the negative key, not the minus key. So negative 1 here. And to get the little blocky letter E, hit the second key and the comma key. So the second key and the comma key will get you that blocky letter E. Okay. All right, so I'll put that in the chat there so it's easy to understand. So second and the comma key here to get that blocky letter E. And then you can put 99 after that, just like so. The upper value here will be, in this case here, let's go back for a second. Okay, so in our example here, we have minus 2.45. So we're going to put minus 2.45 here to be our friend, just like so. And we're going to go ahead and put in paste. Again, we're going to keep the mean here as 0. Standard deviation is 1, since those are default values. They don't tell us what they are. We'll hit paste, and this is how it should look like on your screen, okay? So you should see normal CDF, negative 1 e to the 99, comma, negative 2.45, comma, 0, comma, 1. Okay, so before I hit enter here, I just want to be sure that, everybody's got this on their screen, okay? Or at least has that. And then we'll go ahead and hit enter right after that. And this is the answer that we get here for negative 2.45, so 0.0071, what we get here for this answer. So what's the area to the left of negative 2.45? So this area to the left here would be representative of 0.0071, or again, 0.71% of that. Oh, you got that, Holly? Excellent. Very good. All right. This I like to see. I like to see this a lot. So lots of calculator stuff here today. Working with this together here. So I'm going to go slow over these examples here, so it's not, again, not overwhelming. Okay, so again, at any time, feel free to stop me, and then will we'll go back and see, make sure that you guys got that down. Okay. All right. Before I move on to the next example here, any questions about that one? Nope. Yep. All right. Time I'll go to my main face cam. Actually, I'll go to the subgoal face cam. Let me flipping around. Oh my god. All right. Okay. So that was for negative 2.45. All right, to the left. All right, let's go to the next one here, which is number 7. Determine the area underneath the normal curve that lies to the right of, and this time I'll pick 1.78. Okay, so we'll pick 1.78. All right, so to the right of 1.78. So again, what does that look like here? As a picture, it doesn't really matter here, but again, to the right. So, example here. All right. So, in this case here, we're going to use normal CDF. All right, and we're going to enter in the appropriate numbers in here for this. So let's do that right now. All right, so for normal CDF here, for z equals 1.78, let's go back to our Word document here for a second. This time here, since we're going to the right, above, more, or right, we're going to take normal CDF. We're going to take the lower value here, comma, 1e to the 99, comma, 0, comma, 1, if we're not given a mean and standard deviation. So what I want this to look like here is I want this 1.78, comma, 1e to the 99, comma, 0, comma, 1. Okay. All right, so let's go ahead and do that on the calculator here. We'll hit second in vars here again. Go to normal CDF here. We're now going to put in 1.78 and 1e to the 99, so we'll hit 1. Little block E hits second in the comma key, so second in the comma key. 99. We'll put 0 and 1. And then hit enter. paste. Again, if you have the old school calculator, this is what you want it to look like, exactly what I have on the screen. Or again, exactly what I have written down here over to the right. And then we'll go ahead and hit enter here. So for 0.0375. Hi. So far, so bueno. All right. All right. No problems so far. No problems, no problems, no problems. Let's try another one here. All right, let's try another one here. Let's see if we can put this together here. Yeah, sure. How about to the right? Let's have you guys give this a try here. How about to the right of z equals negative 0.43. So to the right of z, the z-score here being negative 0.43. Let's take 30 seconds here. Once you guys put that down. Okay. Got some good answers there. All right. Anybody else got an answer there? Look pretty good. I ain't gonna lie. Oh, what did... I love how not smart I All right. So again, hopefully you set this up correctly. So how did this look in your calculator here? So I am inclined to agree. I'm inclined to agree. Sorry, I'm inclined to agree with Beth's answer and Natty's answer. That is correct. How did you guys enter that into the calculator there? What'd you do? What exactly did you put? Okay, that's correct. Very nice. Very nice. So negative 0.43, 1e to the 99, and we had 0 and 1. Excellent. Good. That's not too hard. Very, very simple. Very straightforward. All right, good beans. Okay, let's try another one here. This time, though, I'm just going to pull this one from the book here because this has some relevance to not too much new, but again, slightly different. So next example here will be, this time, instead of left or right, let's say it's between. So we'll say between two z values. So between z is equal to negative 0.38 and z is equal to 1.62. Okay, so between z is equal to negative 0.38 and z is equal to 1.62. So in this case here, you have two values already given to you here. So let's think of it this way. What are we going to put here for normal CDF? We're going to use normal CDF here, by the way. That's not going to change. What are we going to put here for our numbers for normal CDF? What do you think? What do we think here? What do you think we should put? All right. Yes. Yes, that is correct, actually. Actually, absolutely true. 100%. Very nice job, Susan. That's right. See, we don't have a lower bound or upper bound. If we say something to the right, for example, of 1.78, that's like 1.78 out to infinity, because that's what 1e to the 99 represents. 1e to the 99 represents infinity. Okay. If we say something to the left, that's like saying, okay, that value going down to minus infinity. That's what minus 1e to the 99 represents. It represents like minus infinity. We can't actually put infinity on a calculator, but we can get pretty darn close, okay? And that's what those 1e to the 99 and minus 1e to the 99, they represent like infinity and minus infinity respectively. If we're between two values, it's even easier because now we don't even have to worry about the 99 parts or anything like that. We can just put those numbers in directly and just plop them in, and we exactly get what we're looking for here. Okay. Does anybody have an answer for me here? What do we get here as our guy? 0.5954. Okay. Good. I agree. I'm just gonna finish it out since I'm already here. All right. Sounds good to me. Nice work. Okay. Questions so far about that? Any questions? Nope. All right. That means easy peasy. Hopefully. Um. Okay. Now, gotta focus on the next question here. So, we found out how to use normal CDF, of course, to find certain areas underneath the curve here, but we also can work in reverse. So let's talk about that. So let's talk about the next thing here. So how do we use the area to find the z-score? So now we're working backwards here. Let's say I give an area, I give like a probability or whatever you want to call it here, and I want you to find the respective z-score that is associated with that. Okay. So a specific probability or area, but working backwards toward the z-score here. So we went forwards here using a z-score to get a area. Now going backwards here, we're going to go ahead and use the area to find the z-score here. And in order for us to do that here, we're going to use the calculator function called inverse norm. Now inverse norm here talks about the area as the mean and the standard deviation. Okay, so the inverse norm, we put in the area, the mean, and standard deviation. Now let's take a good look here at how this is going to work, because there is a distinct difference between, in this case, and I will state it for this case, if you have an older calculator, you have to be really careful about inverse norm. If you have a newer calculator, you could be a little bit more lax with the newer calculator, and that's because of an added function that they put in between both of them, both for this particular option here. So let's take a good look here at this guy here, and we'll look at a book example as well to go along with it. So bring up the book here for just a moment. All right, so let's say, for example, here, find the z-score such that the area underneath the standard normal curve to the left is 0.2. So we'll look at number 14 here. All right, so number 14 is what we'll do next. All right, so the area, if we find, wanted to put that down. Find the z-score. If the area to the left is 0.2. Okay. So the important part here in this particular example is we talk about the area to the left. All right. So this will prove to be fairly vital when we try and find this particular z-score. Now, let's go ahead and go to our inverse norm here. Again, hit second invars. We're going to go to number 3. Okay, inverse norm. Okay. Now, I want to take a look here at this particular guy. And I want to showcase exactly what the difference is. You see this, by the way, the difference between the newer type of calculator and the older type of calculator is this fourth option that says tail. As you see, it has a left, center, and right. If you have an older calculator, an older software calculator, you may not see that fourth option actually appear if you don't have newer software for the calculator. So if you don't see that, do not be surprised. All right, this was a fairly, compared to other functions on the calculator, this was a more fairly recent addition. I mean recent in terms of number of years here, but still a more recent addition to the software of calculators. So this one was added in pretty late, to be perfectly honest. Now, how does it work in both cases? In this case, let's go ahead and do 0.2 as our area. We're going to put 0 and 1 here respectively as our default value since we're not given anything here. And I'm going to leave the tail here as to the left. Now, if you do not see this option here, okay, if you do not see this option here, it will default to the left. It's always to the left, okay? So I'm going to put this here as a text thing, all right? So note, if you do not see the tail option for inverse norm, it will always default left, okay? So that's one thing that you have to understand is that that's kind of one of those limitations that it had before they made updates. Fair enough. Go ahead and hit paste. Uh, and so here, if we talk about what we want, we're looking at negative 0.84. How many decimal places they want, actually? Let's see. Usually go 4 here, but sometimes they want to. You know what? I'm going to go 4 just for the sake of going 4. Because we've been doing everything with 4. So we'll go negative 0.8416. Right? Or just negative 0.84 would be, in this case, our answer for that. Okay. Let's look at the next one here. All right. So let's find, let's do the next same one here. Let's do an example here. Say area to the right. Is 0.44. So the area to the right here. Yes, that is exactly what we're doing here right now, Beth, actually. So we have the area to the right here is 0.44. Okay. So this case here, we're now looking to the area to the right, all right, is going to be 0.44. Now, we're going to do the same thing again, second invars. We'll go to inverse norm. We're going to put 0.44 here. We'll have 0 and 1 here respectively. This time, though, we don't want our tail to be to the left. We're going to be, our tail here is going to be the right, to the, pardon me, to the right. So tail here to the right here is going to be 0.44. So put here to the right, paste. All right, and here we get 0.1510. Okay, so 0.1510. All right. Okay, so here we get 0.1510. Now, you're probably saying, hold up a second. I have an older calculator here. I don't know how to get that same answer that you just got because you just kind of went and did it. You just said, okay, it's 0.1510 and you just got it. So how can I deal with that? Well, one of the things is that if you talk about the area to the right here is 0.44, okay, but your calculator function automatically defaults to the left, then what this implies is that you have to make an adjustment. So this is where for the people here who have the older style calculator here, where things can be a bit tricky because you'll need to do one more extra step here, unfortunately. Okay, if you have an area to the right that is 0.44, an area to the right that is equal to 0.44 also makes one other implication. This means that the area to the left is 1 minus 0.44, or 0.56. So if you did the same thing here, so let me do the same thing here on this calculator, but if you have the older style calculator here, you'll see the difference, right? So if you do the inverse norm here, I say, okay, let's do 0.56, but this time, let's say you have it automatically set to the left because you don't got a choice. Notice I get the same exact answer here, okay? Same exact answer. So if I do it that way because I don't have a choice because my limitation of my calculator function because of just older software, that's how you can make that necessary adjustment there in that instance. Are there any questions about that? I want to be sure everybody's pretty crystal clear about how I came up with those. So we'll do one more example here. Yeah, that honestly speaking, that can be a little bit tough. So want to go through that one carefully there. Because when you do it for like problems with real numbers kind of thrown in there, then yeah, it's definitely a good thing. So no, okay. Now let's do one more example, and then we'll move on. All right, so this one here, I'll just kind of read this one off. Okay. So let me read this one off here. All right. Find the z-scores that separate the middle 99% of the distribution from the area in the tails of the standard normal distribution. Okay, so basically what this is saying is we're trying to find if separate the middle 99%. Can I spell today? No. All right. Yep. There we go. All right. Separate the middle 99%. Now, what exactly does this mean? Is separate the 99%. Now, there's going to be two z-scores here as part of this answer. So we're going to get two z-scores for the price of one. But in reality, we only need to find one of the z-scores here, and then we can automatically assume its counterpart is also true. Now, you're probably saying, okay, well, how do I find those z-scores here? What does it mean to be like the separate middle 99%? What exactly does that even mean? All right, that doesn't seem to make any sense. Well, In actuality, let's take a look at how this actually looks as a picture. Here's the normal distribution. It looks like this. Okay, we're pretty comfortable with that. All this is saying is that find these two z-scores here, where somewhere in the middle this represents 99%. So all this stuff here in the middle represents 99%. So I have a question for you guys. If the middle part here, as you can see in the picture, represents 99%, how much is left over? How much is left over going here and going here? How much is left over? How much do we have total left over if 99% is already taken? 1, right? 1%. Now, I agree. Yes, 1% is definitely right? But remember, let's not forget. So that's one half of the question that I have for you guys. The second half of the question I have for you guys is, now we have two parts and it's symmetric, right? We know that a normal distribution is symmetric in nature. Okay, so it has to be perfectly cut in half. So what do we have here? What's 1% cut in half? There we go, right? So this represents a half a percent here, right? And this represents a half a percent here. Everybody good with that? So the area underneath the curve here, half a percent, well, half a percent as a decimal is 0.005, okay? So 0.005 is another way to write half a percent in decimal. And so this is the area underneath the curve that we need to find in our case, right? So if we do the same thing we just did before, the only difference now is we're going to go ahead and just do, pardon me, 0.005, 0, 1 here. Okay. So let's go ahead and do that here. So 0, 5. Again, I'm going to leave it as a left because, again, I know some of you don't have that option. Paste. And then there we go. We have our, I'm so sorry, not mean to do that. So I meant to do, okay. So here we get our result here of negative 2.576, negative 2.5758, pardon me. So this is our z-score here on the negative side, and we can take its respective positive value as well. It's positive z-score here, positive counterpart. So here are two z-score values here that represent that. All right, there we go. And we got it. Any questions about that? Any questions? Nope. All right. Okay, so I want to note the difference here in this case. I want to note the difference here. These are examples that we've just talked about here. These examples we've just talked about are examples that specifically reflect if we're not given a mean and standard deviation. Now, the other problems here in this section now reflect problems that do have a mean and standard deviation given in them. That's the only difference between what we what we just did now and what we're doing next. Whereas now, instead of putting 0 and 1, we actually have values that we plug in for the mean and standard deviation in these guys. But the approach that we're going to take is going to be pretty much the same. We just have to be very careful specifically about the wording here in the problems. Okay, so let's be a little bit careful here about the wording in the problems, and then we'll be able to see exactly what we'll need to plug in. All right, so let's do some a problem here. Yeah, let's go with yep. Okay, we'll do that one. So I've done this several times. Alrighty. So let's take a good look here at number 39. All right, so let's look at 39 here. All right. I mean, if you gotta, go for it, bro. Anyway. Uh, the bathroom ain't my problem. I'm just gonna point it out that way. Give yourself a hall pass. Size. I know. You gonna go to the bathroom? Not my problem. I'm sitting online. Why does it matter? I'm not where you're sitting. If you have to go, you gotta go, man. I know you just trolling around, but it's still like, bruh. All right. Oh my gosh. All right. Let's look at 39. Oh my gosh. Some people swear. Okay, let's look at 39. Eventually, I'm going to get to 39 here. Chips Ahoy cookies. So the number of chocolate chips in an 18-ounce bag of Chips Ahoy chocolate chip cookies. All right. Mercy. All right. Let's get rid of that. So the number of chocolate chips in a 18-ounce bag of Chips Ahoy chocolate chip cookies is approximately distributed with a mean of 1,262 chips and a standard deviation of 118 chips, according to a study by cadets of the U.S. Air Force Academy. Yes, because we spend all our military dollars figuring that out. I know. Anyway, so letter A. What is the probability that a randomly selected 18-ounce bag of Chips Ahoy contains between 1,000 and 1,400 chocolate chips inclusively? All right, so, you know, I like cookies. I like Chewy Chips Ahoy. Chewy Chips Ahoy is my favorite. I don't know about your favorite Chips Ahoy cookies, but if there's one cookie that's pretty good, it's definitely that. All right. So, how do we figure out this probability between 1,000 and 1,400 chocolate chips inclusively? What are we going to do here? How do we go ahead and solve for that? What should we use here? Crunchy Chips Ahoy are the correct choice. Some people like crunchy, some people like chewy. I'm a big chewy Chips Ahoy fan. I ain't gonna lie. I don't eat them often, but if I do. Hey Jade, how you doing? Ready to help me with some math here, Jade? I hope so. We're learning about Chips Ahoy cookies. chocolate chip cookies. Trying to figure out some probabilities with some chocolate chip cookies. So what are we going to use here, ladies and gentlemen? What are we going to use here? You bad at math, good with cookies? Excellent. Well, we're talking about chocolate chips specifically. Figuring out the probability of getting a bag that's between 1,000 and 1,400 chocolate chips. There's nothing wrong with a little bit of chocolate in your life. Nice snack to have every once in a while. So, what should we use here to solve this problem? Just talked about it here, so again, we have our couple of choices here, guys. Remember, this is normally distributed, so you got two choices here. You either use normal CDF or you use inverse norm. Okay. Normal CDF. All right. Wait, James has a secret second channel? Oh, I gotta know this. All right. Just send it to me on Discord or something. Normal CDF. All right, what are we going to put down for normal CDF? What should we put down here? What numbers are we going to use here for normal CDF? What numbers should we use here for normal CDF? Come on, guys. Okay, 1,000, 1,400, 0, and 1. Okay, so I agree with the first parts here. This time, however, remember, as I said here, this time we actually have certain data here. So we actually have a standard deviation. All right. So what's that going to be here? We don't want to put 0 and 1 here. Oh, yeah, that would be helpful. How's that? There we go. Let me make this a bit, oh, wait. Let me move my big face out of the way. Switch over. There we go. That's a bit. There we go. That's better. So what two numbers here can we put in for the mean and standard deviation here? Sorry about that, Susan. You're right. $12.62 and $1.18. That's correct. So here, this time, we're actually given a mean and standard deviation. We're given a mean and standard deviation here of 12.62 and 1.18. So now we want to enter this into our calculator here, and then let's see what we're going to get here. All right. Again, this is for probability, again, between 1,000 and 1,400. All right. So plugging this into the calculator here, let's sort this out. Can you cooperate with me? All right. So helpful if cooperate. All right, so that's correct here, 0.8657. Very good. All right, let's look at the next part here. This was just part A, but we have a few more parts to go. Let's take a look at the next part here. Part B, find the probability that the randomly selected bag contains fewer than 1,000 chocolate chips. So fewer than 1,000. So now I just want to make one note here about fewer than 1,000. We're going to include 1,000 here, by the way. So technically it'd be like 1,000 or fewer, but because it's a continuous variable, we don't go down to 999. So do not use 999 here, by the way. So just to let you know. Don't not use. All right, can anybody tell me how we could write this one up here? So we have, again, the same mean and standard deviation. That stuff is going to stay the same. But what should we put here for fewer than 1,000? What should I use here then? What should I put in for this problem here? Give you guys a minute to think it over. Put your answer there in the chat about what should I enter in the calculator. The standard deviation here was 118. So I'll put this here on the screen. So, oh, well, it'd be helpful if you could actually see it. That would be pretty helpful. No wonder why you can't see a thing, because I'm being an idiot. All right. Yeah, I'm like, oh, yeah. Normal CDF, 1,000, 1,000. Okay. So I don't want to put 1,000 twice. I need a lower and an upper value here. So that's correct. Okay, so that's correct, Mazdi. That is correct. Normal CDF, because we want less than 1,000 here. So we want -1 e to the 99, 1,000, 1262, and 118. All right, so that is correct. Okay, that is exactly what we want here. But I'm gonna switch to my no face cam here. See the whole screen then. All right, so this is what we have here then, and we're just gonna go ahead and go to our normal CDF here. All right, we're gonna have, again, -1 e, so -1. E is the second in the comma key. The second in the comma key to get the blocky E. 99. Put 1,000 here. 1262, 118, and we'll go ahead and hit paste. 1-0 make more sense? Yeah, in all honesty, it makes perfect sense to me. It doesn't matter which one you actually put in. Mazdi, you could put -1, e to the 99, or 0. Either case, you will actually, you'll get the same result in either case. So the reason why I keep it as -1 e to the 99 is because of the fact that it's It's again it's again just keeps things consistent. That's all. Okay, and so what do we get here? We get point 132, 0.0132. So okay, so that's what we get here for that answer. Let's do another one here. Okay. So that one's kind of yeah, all right, we'll do that one. Probability of more than 1200. So it's probability of more than 1200 chocolate chips. Probability of more than 1200 chocolate chips. Again, do not use 1201. All right, so just put that as a sidebar here once again. We're gonna note not use 1201. All right. What should we put here for this one? How are we gonna get this guy? Okay, that's correct. Very good. Right? All right, excellent, both of you. Wonderful. So we have 1200, 1e to the 99. We have 1262 and 118. Nice. All right, let's put this into our calculators. See what we get. So we get normal CDF here. We get 1200, 1, second, and the comma key. Block E, e to the 99. 1262, 118, and we'll paste it. See what we get. All right, so 0.7004 is what we get here for this one. I am gonna show off. I wonder. Yeah. Okay. So I am gonna show something off here, by the way. So this isn't gonna be involved with you guys at all, but just to showcase something here. Sometimes in the book here, and I'll actually go on my camera. Just have just a little bit more to go, guys. I promise. That's correct, Daddy. Right. That's why I set it up that way, because then it'll be easier for you to follow along with. So you have negative infinity for one and then positive infinity for the other. That's right. Cuckoo. All right. So what it says in the book here, I'll show you the answer here in the book because I have the instructor's edition. For letter C, for more than 1200, they actually listed as specifically, this is the book here, they listed as 0.7019. There is a little bit of a discrepancy here between the answers in the back of the book and then the answers that we actually get here via the calculator. Always trust the answers you get via the calculator. They're more precise and they're the ones that my math lab will accept. Okay, so just letting you know now, if you're using the book as like a little bit of a reference here, there is a bit of discrepancy here. But the ones that you should be using here is the ones that you get on the calculator because they're the more precise ones at the end of the day. They use the proper tables there. The reason why there's a little bit of a discrepancy is because it uses the back of the book, which has some rounded values. So it may be minuscule, but again, um, don't like fret over the fact that they're using rounded values in the back. Use the ones that you use for your calculator. So, um, yeah. letting you know about that. All right, one more example. I promise you, one more example, and then yeah, things. Yes, and things. Oh baby, baby, triple. Okay. We're gonna use the same thing here, by the way. Same stuff. So let's do all right, so this is kind of like a little bit of an extension here. Determine what oh actually I should say this. How many? Hello, mate. How you doing? How many chips would be in a bag in the 75th percentile? So let's answer this question here. How many chips would be in a bag in the 75th percentile? So if you see a question like this, or it could say quartile, like the third quartile, we talked about that before, but if it gives you a percentile here, this is essentially asking you about the area underneath the curve being like, say, 0.75. So again, the area here is equal to 0.75, okay? That's essentially what they're asking you here in this case. How many chips would represent the 75th percentile? So what should we use here to find those number of chips? What function on the calculator should we use here to find the 75th percentile here, or the area being 0.75? What should we use? So we should use inverse norm. Okay. So let's use inverse norm for this. All right. How many chips would be in a bag in the 75th percentile? The area here being 0.75. We're going to use inverse norm here. So we're just going to put 0.75 as our area here. And again, we're going to go ahead and put our mean and standard deviation that we used from before. So we're going to use 1262 and 118. All right. So let's see what happens on the calculator. See what we get. Again here, if you do have the option of tail, just set it to left. If you don't have it, don't worry about it. You're going to get the same answer anyway. All right. And so for our case here, we get 1,341.59. Okay. Well, I'll go 5898. Let's go to 4 decimal places again anyway. Just depends. But here you go. So about 1,342 chips if we were to round up, for example, or 1,341.5898 chips would represent the 75th percentile here in this instance. Are there any questions about how we went ahead and applied this? So I hope that this made sense here about how we're able to apply normal CDF and inverse norm here and this kind of stuff here. So how do we know how to use inverse norm? Excellent question. So the way you know how to use inverse norm is that inverse norm here, inverse norm is going to associate with a particular percentiles. So if it asks you, hey, what's the date, what's the number of chips associated with the 30th percentile, or what 50%, 54% represents how many chips. Okay, when you see that percentile, that should be, or area, whichever way you want to call it, that should be a dead giveaway for you to use inverse norm for those problems. If it wants you to find a probability, you're going to go ahead and use normal CDF. Okay, so probability, normal CDF. Percentile equals inverse norm. Okay. All right, so hopefully that makes it crystal clear about which avenue you want to go down, depending on the problem that you're given. Ooh, you're welcome. Just be a little careful about the wording there, but again, you may run into a couple of issues, so that's okay. We can go over those. All right. Let's put up a poll here. So let's put up a poll here. It's a very legitimate poll here. I'm asking an honest question. That's all. I went overtime. Are your brains fried? I did go overtime here. I kind of neglected the break here, so I don't know if your brains are shish kebab fried after laying down a lot of stuff. So everybody's got a thing. So got a half and half vote. Wow. Some people like, yeah, man, feels good, dude. All right, so it looks like it's a half and half vote. Man, holy cow. Right down the middle. Respect on that. Respect. Okay. Well, I'll do one more example then. One more example. Just to showcase one more thing then. Since it's half and half. Then I'll make this the last example and then call it good. So we'll use the same information as before, by the way. So nothing will change in terms of the mean and standard deviation. So this one here will go by a little quick, but again, has its importance. So this one here says determine the number of chocolate chips in a bag that make up the middle 99%. So chips in a bag that make up the middle 99%. So basically, all this is asking us to do is to specifically go ahead, and again, just taking a look at our picture here, if you remember, we did this picture just not too long ago. It is we're going to get two values here for the number of chips. We have this 99% in the middle here, And you all said that we took a 0.5% on each side to make up that last 1%. So what we want to look at here specifically is, we want to look at two areas here. First of all, we want to take a look at this guy here of 0.005. Now, we're not trying to get two z-scores here, because then we could easily just do it without too much trouble. But we're also going to want to find this percentage right here. So this is 0.005 for 0.5%. But this percentage right here represents 99.5%. So we also are going to use the other decimal here of 0.995. So if we want to find the number of chips that represent 0.5% and 99.5%, that's exactly what we're going to do here to get our answer for this problem. So in this case, we're going to use inverse norm 2 times to get two different values. We'll use inverse norm here for 0.005. 12, let me see, what is that, 62? 62, yeah. So 1262 and 118. Okay. And we'll also do the same thing here, inverse norm. And we'll do 0.995, 1262, and 118. So we'll have two different inverse norms going here, which will represent both sides of our answer here. So let me quickly do this on the calculator. So 0.005, 1262, 18. All right, so this first one here, I got 958.0521. Okay. And then I'm going to do it again. Let's see here. 0.995, comma 1262, comma 118. And so here I get 1565.9479. So if I want to classify the middle 99% of chips in a bag, it would be from this value here, 958, to 1565 or 1566. So 958.0521 to 1565.9479 is what we have here for this guy. All right, that represents our middle 99%. Any questions about that? I hope that last example made that last part a little clear. So, any questions? So whenever they ask the 99%, so Natty, that refers to the middle 99%. So notice here we talk about the middle 99%, but then we have 1% left over. So we have to cut that 1% in half. So that's why we have 0.5% on the left and 0.5% on the right. So this represents 0.5%. This is what this line represents. This line represents the 99.5% percentile. 0.5% plus this 99%. That's what this line represents. So that's why I use 0.995. This can be different here if this middle percentage is different. If this was, say, 95%, so let's say that we had this middle part here, and this middle part here happened to be, say, 95%. Well, I need 5% left over, 100 minus 95%. So I would have 2.5% here and 2.5% here. This line here represents 2.5% or 0.025. This line represents 2.5 plus 95%. This would represent 97.5%. So this would be 97.5% here, or 0.975. So these would be the two values I would use if, for example, it said the middle 95%. So all right, cool. Any other questions? Nope. All right. All right. If there are no more questions, I want to thank all of you once again for coming out on here to the stream today. All right. Nope. All right. Thank you so very much for coming on out here to the stream. You guys are absolutely 1000% wonderful people for coming on out here and sitting with me late at night. You guys, I hope if you guys have questions, feel free to email me. You know where to find me. Not very hard to find, to be honest. All right. Everyone, have a very wonderful night. Okay. As always, everybody, stay safe, stay healthy, and most importantly for everyone in this room, stay sane. All right. Have yourself a wonderful night, everybody, and we will see you here on Wednesday, same time, same place, everybody. I will be here. All right. Take care of yourselves. All right. And we will see you later. All right, everybody. Take care. Bye. Bye, everybody.